Okay, here we go. This unfortunately is take two of a video on how to accurately model depreciation in a corporate model where you have some historic assets. Now, the first problem is that uh, to model things accurately, you would like to find the historic growth rate um, of of the assets. This model called financial model function library, of course, in edbodmer.com, like the other ones. Where did I put it? We'll put it here, and we'll put it there. It's going to be all over the place. It'll be in the corporate finance, because we use a lot of corporate finance, acquisition, project finance, or the financial functions are relevant to all of these things. Now, this financial function here, let's just see that the issue is it's like you're peeling off trees. If you're given here, let's change the growth rate to 8%. Now, if we change the growth rate to 8%, our stable ratio of accumulated depreciation to a plant changes. If we would change the growth rate the lifetime of the assets to 10 years or 12 years, then the ratio changes as well. Let's make it 5 years. Then the ratio is 36.93, and if we make the growth rate higher, it goes down, and if we make the growth rate lower, it goes up. So the issue is you can use the ratio of accumulated depreciation to gross plant along with the life and the growth, well, along with the life, to back out the growth. And there's a little function that does this. So I think this function looks right now to the computed depreciation ratio in the life, and then it just essentially does a goal seek on the growth rate. So if I put 10% growth rate or 9.86% growth rate, it computes it. We could put more decimals in. If we put 20 years, oh, the growth rate didn't change. Okay. The accumulated depreciation changed. Okay. I put negative 5%, it goes. Okay, so let's see how this function works first. Now, to set it up, we'll just do it in Excel without the function. We'll just take our base capex, doesn't matter what they are, and grow them at our growth rate. Okay, shift control right, arrow control R. We put our capex in just from above. Okay. Opening balance equals closing balance. Retirements. If this number is less than or equal to the life, then we put our offset. We go up 1, keep it at 0, put a minus on the life, and then we're finished. And I said if this thing is greater than or equal. Okay. And then we can compute our depreciation as the opening balance multiplied by 1 divided by the life. I didn't need the brackets. And then finally, the accumulated depreciation is the opening balance equals the closing balance. We take our depreciation, take our retirements, and our closing balance is our opening balance plus depreciation minus retirements. There we go. And the accumulated depreciation ratio to the gross plant is from here. So that's our stable ratio. Okay. And now, of course, we could make a goal seek. Data, What if analysis goal seek? Let's set this to 0 by changing the growth rate. So then we get exactly our 40%. If it's not exact, we can go to File and Options and Formulas. Whoops. Looks like I have quite a few iterations already, so I'm not going to increase those. Goal seek might go kind of wild. Okay, so instead of doing the goal seek that way, we just make a function. This function is named part of the depreciation rate. Excuse me. It's part of the depreciation rate functions. I'm going to edit, and this is the one called find growth. And here's how it works. We put in a accumulated depreciation, a lifetime. I made an optional variable for converge. I'm going to make it converge without the E. And if you didn't enter a number, it just gives you a default. Then we put our and let me change it down here. I hope watch me mess everything up by doing that. Then we put a starting point for our growth. We're finding the growth, so we're going to put a minus 100% up to positive 100%. If it's outside that range, this won't work. And this next increment will allow us to change the growth rate increment we put in our for loop. We make a for loop that goes from the start to the end, and we step around an increment. Now in the first one it'll just be 1%, and then we go through and we put some initial values in, which we have to since we loop around the years, and then we compute our depreciation expense, our balances, get our ratio, and it stabilizes at the end of the life. That's the whole point of this stuff. And then we compare our computed ratio to our what we entered as our target. Now if we exceed the ratio, then we go back to the next increment and we put a much smaller starting and ending point. That's the whole idea of these user-defined goal seeks you can make. There's probably some kind of mathematical name for this. And then we just go around until we converge. Okay, let's see if I put that converge thing in, it still works. Okay, so let's say we change the growth rate to 7.25. All this is doing is it's checking to make sure it all works. Okay, now let's put this into our other model where we left off last time. We had some depreciation methods that didn't, they worked, some of them worked okay, but they're not really accurate. So we'll put our depreciation method for using functions. I was going to say user-defined functions. And to make our to make the process work, let's begin the process by finding the growth rates and all that. So why don't we put the parameters? Okay, and let's first put the life of the project. Let's just go up and get the life. Okay, and the life is 12 in this case. And let's get the and let's get the accumulated depreciation from the history. And that is, we put match, let's match the last historic year. Again, this is pretending that you take this against the period, so that means we're in column 18, and we'll put an index around that and find the where is this, our accumulated depreciation around that. So that's our accumulated depreciation to net plant. If you remember, We actually have to press this to have a little bit of a circular reference issue here. Okay, so once we do that, Shift Control 5 with a, if this, I put some menu things in here too. That's in the financial function library, but I'm not going to use them right now. And then we can put implied historic growth, because we would have this from our financial statements. We could easily find this, and now to put this here, now you could make an add-in and put this in our add-ins, but instead I'm going to go to our other financial function library where we had our find growth function, and then I'm going to put it into this. Let's make a let's put it into this function. Now you remember we already had this base growth function, so let's just put this one in and get the equal find growth, and we put in first the accumulated depreciation ratio, and then we put in the life, and the other one's optional, and we get, this is irritating me, that it gives a tiny bit of a different number. That might be because of the goal seek. We didn't have a perfect goal seek thing on here. Let's just try this. Options, formulas. Got a whole bunch here already. I'm going to make one more though. Okay, so I can't get that difference to be absolutely 0. I'm not going to worry about that. Alright, and that now, once we have those parameters, we can also put the base retirements. And that we're just going to go look back 12 years and start retiring, and this was this find base thing that we had down here. Okay, tab over, function, growth rate, and the life. Okay, and that's our base percentage. Now to get this thing working, let's put the existing depreciation in first, and let's put our opening balance, and then put less the retirements. And our retirements are going to be our base value. We're going to, the gross plant in the base year multiplied by this thing, and then we're just going to increase this over time. Let's see if we can make an elegant let's see if we can make this. So as usual, the closing balance is, if it's the historic period, we take the actual closing balance of our plant. Otherwise, we take the opening balance minus the retirements. For me, that's just such a crucial idea. Now let's show you that one. So this was if it's the historic year, then take the actual. Otherwise, opening balance minus retirements. So far we have nothing in our future year. Of course, our opening balance equals the closing balance, and now we have our challenge. So let's see if we can do that. If it's the if it's the actually, if it's the first modeled year, I'll do it with this one first. I think we'll need a no, we're going to need another switch for the first. let's put first period. Yeah, let's go period. Okay, and that's going to be the when the year equals, I guess, why don't we put the last historic period plus 1. Okay. We should have made a conditional formatting on those true and false. So if it's the first modeled period, then here's what we do. We take the gross plant, which was, I guess it's the opening value of the gross plant, and we multiply that by the base retirements. Otherwise, we take the last one and multiply it by 1 plus the growth rate. Okay, and let's see what happens here. So here's our retirements, and you know, this was 12 years. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and this 210 down here is exactly the same thing. So we were able to model our existing retirements. If we look at the actual retirements, they were 11.77, and we had 11.76. I think that's close enough. That's because we had our growth rate wrong. And then we can put our depreciation on existing plant, which is just the opening balance multiplied by 1 divided by the life multiplied, let's just do this only for our modeled period. Okay, and then we can put our, so that's our existing, and now we can separately model our new plant. Okay, like a lot of people do, and we put our opening balance, add the new capital expenditures, and less retirements on new plant, and get a closing balance, and then we'll have our depreciation on the new plant, and we have our total modeled depreciation, and then we can look at our, compare that to our theoretical depreciation and see how close we are. Alright, so as usual, you have our opening balance equals our closing balance. The new capital expenditures, or if it's the modeled period, then we go up and get our actual assumed capital expenditures. If the year is greater than or equal to our life, then we have an offset, and we go up to our capital expenditures, keep them on the same row, and put a minus on this one, and then our closing balance is our opening balance plus the capex minus the, oops, am I not showing you everything? Excuse me for that. And then so that's our new plant depreciation, or plant balance, and then this is the opening balance multiplied by 1 divided by the life of the, whoops, what happened here? I switched to French again. Okay. Depreciation on a new plant is the opening balance times 1 divided by the life. Okay. F4, and oof. Okay, that's all we need to do. Oops, I'm again outside the range, excuse me for that. So that's our depreciation on our new plant, and our total model depreciation is the sum of these things. Okay, and we can put our theoretical depreciation that we derived from everything else. Okay, oops, I'm off the sheet again, and this time we're matching just right. Now I think there's one little problem here left over. If let's make the historic period much bigger. Let's just make a really long-term period. If we would do this, okay, what happens is eventually our existing plant balance goes to 0. So our retirements have to be, this is a little bit of a long formula, I'm sorry for that, but they have to be the minimum of this formula or the opening balance. So we have kind of a classic minimum problem. I really don't like the length of that formula. But I'm going to leave it for now. Okay, and so let's make sure that here then our retirements go to 0, and we have the, whoops, oh no,